So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar about an advanced axial fan simulation. As you know, at CFD Support, we develop and maintain a comprehensive engineering simulation environment called TCAE, which is based on open source and which has an exceptional value cost ratio, and it will be our pleasure to show it to you in action in today's webinar. Well, I hope everything is working just fine. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and the recording will be made publicly available on YouTube. So yeah, you can see all the details later on. If you like, at the end of this webinar, there will be a Q&A session dedicated to your questions and our comments and answers. So feel free to ask your questions anytime during the webinar. I think you can find easily a question form in the menu. So yeah, you can ask your questions. All the relevant questions will be answered. Some questions will be answered right away in the webinar, and the rest will be answered later via email. So I guess this would be it from the very first slide, and I think we are ready to get to the action. So please let me quickly introduce the webinar speakers. So this is me. My name is Luboš Pirkl, and my current job at CFD Support is telling the world about us. And right next the door is sitting my colleague Radek Máca, who is our head engineer and senior developer of the methods and benchmarks and everything. And let's check if he's really there. So hello Radek, what are you there? What's up, man?
Hello Luboš, and hello all the viewers, listeners, and attendees. Yeah, I'm really fine, and it's a pleasure to see so many people here online. So it's great.
Okay, well, so yeah, I guess, yep. Well, are you ready for the webinar?
Yes, I am ready.
Okay, thank you. So we are looking forward to your contributions. So I'll continue with the introductory part. Actually, here is the very simple agenda of today's webinar. So in this first part, I will give a brief introduction about what's going on and what's on the table. Then in the second part, Radek will give a live step-by-step example how to make a complex analysis of an axial fan inside TCAE environment. And in the third part, in the last part, there will be a Q&A session dedicated to your questions and our answers. So I'd like to ask you once again to ask your questions anytime during the webinar. Some questions will be answered right away in the webinar. The rest will be answered later via email, but you can be sure that all the relevant questions will be answered because yeah, we are interested in your feedback, and it means a lot to us. Okay, so yeah, so let's start with a very quick introduction. So our company name is CFD Support. It was founded in 2009. It's located in Prague, Czech Republic, and at CFD Support we deal with engineering simulations at all levels. We primarily focus on the development of CAE software with very high added value for its users. It's definitely high-end vertical software, and our clients are CAE professionals who know well what they want. We are obsessed with accuracy. Accuracy is of our highest priority, and besides accuracy, we are focused on automation, repeatability, and efficient workflows. We don't believe in general purpose codes. Specifically, we don't believe that any particular software can accurately simulate everything or that anyone can simulate anything. We do believe that any successful engineering project is a result of focus, skills, experience, patience, and dedication. We believe in open source, especially we believe in a combination of open source and professional technical support. So far, we have invested more than 30 many years aggregated of focused team development on top of open source to deliver professional simulation tools like this, and that's why we are being picked. Yeah, so here is what's on the table now. It's TCAE. This is you can see now its graphical interface, and I guess you know already, but still TCAE is a comprehensive CAE engineering simulation environment. It has successfully merged the benefits of open source with the benefits of commercial codes. So due to the open source nature, TCAE is unlimited and extremely flexible, and due to the commercial code nature, it has a graphical interface, it has professional technical support, it has documentation, it's robust, it's accurate, it's automated, it's well tested, and it's ready for use in the industry. This is how the current graphical interface looks like. The user can do here everything from the simulation setup and the simulation run to the detailed post-processing of the results. And of course, besides graphical interface, the batch mode is available, but we will speak about it a little bit later in the webinar. And yeah, I guess it's obvious that TCAE can be run in the terminal, and it can be run by another software, or it can be used inside bigger simulation chain. So I guess that's pretty obvious. I'll continue. Yep, as already mentioned, TCAE has individual modules. We say it has a modular character. It consists of software modules that can be combined according to the project needs, and you can view the individual modules as a standalone software pieces. So it's not a one program. It's a couple of quite independent standalone software pieces. That's quite important. The user can choose between TCAE modules, and if needed, combine them with many other software pieces available in the market. So I don't know, for example, speaking about rotating machinery, a user can design a fan in CF Turbo. The mesh can be created in T-Mesh. The CFD simulation can be done in DCFD, and structural analysis, including FSI, can be run in the FEA module and combined in such a way. Or, for example, the pump can be created in cases, and once again, the mesh can be created in Grid Pro or Pointwise, and just CFD simulation can be run, and all the software pieces can be used in any combination. So it's extremely flexible, and that's why we say TCAE has a strong integration ability. So it has been from the beginning developed in a way to fit any existing workflow, no matter if it is combined with commercial codes or in-house codes or with another open source code, because it has strong interfaces. It's very flexible. I guess it's obvious that in any typical enterprise, the engineers usually have some existing workflow already. So TCAE is capable of fitting into it, no matter what design tool is used, no matter what CAD tool is used, no matter what meshing system is used. TCAE is still here to fit any workflow, do the simulation, deliver the results for the user's judgment, and be helpful in a way, because it's unlimited and very, very flexible. Yeah, so it's ready to fit very complex workflows at any product design stage. It's ready for large simulations or for little or small quick simulations. It's ready for optimization loops. It's ready for cloud computing, for example, and many other trends going on out there in the market. And There are real tutorials and benchmarks and everything. And yeah, so TCAE is very flexible, and everyone can create his own workflow that fits his best purposes, skills, needs, and resources. So it's flexible. TCAE is also unlimited, so there are no limitations on the number of its users. There are no limitations on number of job scores and processors, nor hardware installations. All these things are unlimited. So the users or its users can use their resources to the fullest. That's very important. TCAE is accurate. It's definitely very accurate because it has a clear focus and purpose. It's aimed especially on turbo machinery applications, and later it was extended to external aerodynamics. It's definitely not a general purpose code. It's aimed on accuracy, and we are ready to prove it. Over the time, we made a lot of benchmarks, and some of them are available for public presentation. So we are ready to show it. Okay, yeah, sure. So yep. So TCA is from the beginning developed in a way to fit the modern engineering workflows. So it's fully automated. So it can be used either as a black box. So the user puts the data in, TCAE does its job, and the user just picks the results at the end. Or TCAE can be used as a highly sophisticated software, CAE software, where all the options are open. And I would say that the beauty of TCAE is that it's the user who decides how deep to dive into the details, or not at all, right? It's flexible also in terms of users' skills and experience and everything. Okay, so we believe in the importance of the technical support. Support is coded in our DNA and also in the name of our company, after all. And for more than 10 years, we have supported the engineers in achieving their goals, and we are obsessed with professional technical support. We have special process for it, which is powered by the OS ticket system. The CAE is natively compiled for Windows and Linux operating systems. There is no need for any virtual systems at all. The engineering workflow is exactly the same on both systems. So our typical user does the case setup and first tests in Windows operating system, and then she or he moves with TCAE on Linux clusters to use it on multiple cores or processors to fully benefit from the fact that TCAE is unlimited on number of processors and everything. So these two same operating systems, yeah, the remote access is of course possible in batch mode and scripting and everything. So yeah, TCAE also includes a fully automated meshing system based on SnappyHex Mesh and NetGen, and also the external meshes created in another software can be loaded in it, right? So we always leave this mesh decision up to the user. Some users prefer automated meshing based on SnappyHex Mesh and NetGen. The other users prefer external meshes created in the third-party software and loaded into TCAE. So that's fair enough. We fully respect that. It's always up to the user which or what meshes are going to be used. TCAE has strong post-processing capabilities. Every simulation that's executed in TCAE has its own HTML report and PDF report where the results are presented, and whatever you run in TCAE, it has a report. That's very important. You see when it was simulated, what was simulated, what are the results, and volume fields are processed and visualized in ParaView if needed, and the integral results are also saved in CSV files. on the hard drive for further post-processing purposes if needed. Yeah, there are special turbo machinery post-processing tools like Meridional Average or blade-to-blade view, but I'll go ahead with the presentation. Okay, so as I guess you know that no software is ever finished. TCAE remains under continual development. The development is users driven, so we continually gather the requirements from the TCAE users, we evaluate them, and we keep adding them into the new version releases. We use a special system for code development in a team called GitLab. I guess you know it, it's very popular and extremely effective. TCAE will keep its modularity for forever. It's been decided at the beginning. Regarding this, we have now two ways of thinking. It's the horizontal way of thinking. So in the horizontal direction, we keep in mind adding new tools, new software modules, and the complexity. And there is a vertical way of thinking, a vertical development, which is adding new applications, new capabilities, and new high-tech methods for existing modules. So it's our two way of thinking of development. Maybe I should mention them, but very quickly, the main applications. TCAE core business has always been turbo machinery simulations. So for example, a simulation of pumps. TCAE can simulate many kinds of machines, all the sizes, both radial and axial types, both compressible and incompressible fluid flows, pumps, of course, fans and blowers. Yeah, axial fan is the topic for today's webinar, and also hydro turbines are very effective, and compressors and turbochargers and wind turbines. Yeah, and later what had worked so well in the turbo machinery field, we decided to extend to for the external aerodynamics to simulate cars and the aircraft, and also all the other stuff like the internal aerodynamics of various valves and hydraulic valves, and also manifolds and intakes like the intake manifolds and various exhaust manifolds and piping systems. TCAE shows fantastic performance when simulating propellers like ship propellers or the whole hull propellers and other kinds of combinations of external aerodynamics and turbo machinery. Yeah, also the wind loads acting on the building surface are quite effective, and yeah, recently we've added a module for simulating human comfort in a room. But in today's webinar, we'll definitely, okay, I have a couple of benchmarks, but I'll go very quickly here. It's not that important. The time is passing very quickly, so I'll stop here. Today's webinar is about an axial fan simulations. So we have prepared a complete complex workflow, very complex workflow, where is actually the fans can be created based on the documentation. We used a special module called TCAT. TCAT is very special, and it's a new module, and it's always delivered based on a consultancy basis. So it's always delivered on an individual basis. So yeah, just from parameters and let's say from the blade slices, a new the geometry can be created, and the rest is done by our typical modules, which is T-Mesh. So T-Mesh creates the simulation mesh both for CFD and FEA. Yeah, the CFD simulation is run in module TCFD, and the FEA simulation is run using the module TFEA, and which includes the FSI module as well. So all the process is fully automated, and it can be run in a loop if needed, and it's very effective for this reason. Okay, so this would be actually it from me at the moment, so in the introductory part, and I would like to ask Radek. Radek, how are you?
I'm still fine, very fine.
Okay, so are you ready to take over?
Yes, yes, yes. Please make me a presenter.
Okay, so I'm handing over the presentation over
Okay,
to you.
show my
So
screen, and
okay, we can see
can you
it.
see
Yeah,
my screen? Yeah,
yeah,
perfect.
yes, please go
So
ahead.
thank you,
Yeah.
Luboš. Thank you, Luboš, for your part. And now we will go into the practical part. So we will play with the Axial fun case, and we will start from very beginning. So as Luboš already mentioned, almost all information can be found on our webpage, cfdsupport.com. So for today's case, you can go for TCAE menu, and here you will find the Axial fun item. So if you click, so here you will find all the information about the today's case. You can find a PDF report of what has been done and how, and you can download the case. You can anytime you can ask for a trial version. So we will provide you a trial version to play with our software on one of the tutorial case, or you can also play with your own geometries and try to simulate your particular problems with TCAE. Yeah, so for more information, you can go here to find a description and what was simulated and how, and of course for the source geometries and source setup of this case. So today I will start from very beginning. So I will locate this case. So if you ask for a trial version and install TCAE, you will also find automatically this case. So so there is no need to download this case because it is automatically placed in the tutorials within the installation. So here Axial Fun Stage webinar will be our place, our working place for today. So what do you have at the beginning? I have already simulated something, so this is not default view of the working case. But what are the inputs? So the inputs are the preset TCAE file. So we don't need them today. I will start from very beginning. But what we need is the input geometry, which describes our problem. TCAE, and for TCAE purposes, you can load the mesh, some external mesh in MSH format or CGNS format, for example, or you can make your own mesh, computational mesh from STLs by using SnappyX mesh with our own interface. So let's see how the input looks like. So I can go, for example, how the rotor looks like. So I will click, for example, one of the STLs. So now the paraview and the GUI for TCAE will appear. So here, for example, I have clicked the geometry for FEA analysis. So this is the solid of a blade which we would like to analyze in sense of structural analysis. And for safety purposes, we need to have the closed domain where the flow is simulated. So this is the typical, let's say, typical geometry to simulate axial machines, axial fan. So we have only one segment to be simulated, as you can see, and it is closed in the periodical segment, including one blade only. Before we go for the meshing, I would like to emphasize some general inputs requirements because they are not generally known, and particularly for TCAE purposes and for meshing purposes in TCAE. So let me go to the slide where it is bit explained. So I will go very quickly. Yeah, so we can put the external mesh if you have any external tool like GridPro or Numeka or any other meshing tool. So you can generate your own mesh in any software and then input the resulting mesh which is ready for CFD simulation. Or you can put the STLs which define the computational domain. What are the main parameters of the STLs? Now I will be exclusively speaking about the STL. So you need to input only the data which somehow describes the flow path. So it somehow it can be called the fed surface. So the surface which is touching by the fluid. I think this is clear. What is very important that if you get from some engineering department, you get the CAD, including all the screws, all the solids. So for CFD purposes, you just need a simple, smooth domain which describes correctly the computational domain. So this is the first and somehow very boring part, to cleaning the geometry. So this must be done in advance in some CAD, in your favorite CAD software, and clean the geometry and export the STLs. So then the STLs should be also exported in the way that follows so-called component thinking. I think it's pretty straightforward. So for any geometry can be split into meaningful parts. For the turbomachinery cases, into the rotating and non-rotating parts. So as this example shows, for example, the radial pump machine can be split, for example, into the four parts: into the inlet pipe, rotating part, including the impeller, for example, volute, and outlet pipe. So during preparing the STLs, you have to also prepare all the parts, mainly the interfaces, not the part of the CAD, because there are no solids which are dividing these parts. So for example, interfaces has to be added and exported separately. Then each part cannot be defined as one STL, because the STL define also the patches, the part in the computational domain, and each part has to be assigned a special boundary condition to build the CFD the CFD problem, to define the CFD problem properly. So each component has to be also split into meaningful part. Usually, if the flow goes in and out, there must be inlets and outlets. If some part is rotating, if some part is not rotating, then also the STL has to include the rotating part only, and another STL should contain another non-rotating parts. And also, for example, from meshing point of view, to be more flexible, then we can also split, for example, the blade itself into the leading and trailing edges, suction and pressure side. So then we will be able to clever define the level of refinement, for example, much more high level of refinement on the leading edge, and rougher level of refinement for the flat parts like suction and pressure side. The same holds for hub and shrouds and other meaningful parts. So if you split it into more parts, then you have more free hands in definition of the problem and in definition of the meshing parameters. The same holds for the interfaces. So interfaces are parts which connects to neighboring component. So it is always a couple. One side is holding by one component, and second part is owned by the neighboring component. And if you put everything together, these interfaces must be aligned perfectly. For example, interface between rotating part and volute here. So it must be connected perfectly. There is an exception for axial machines, or for the machine where you can define some rotational symmetry. So then you can save a lot of cells if you simulate just a segment of the full wheel geometry. And in this case, the interfaces must be aligned in the sense of the full wheel geometry. So there is there is no difference if you place the stator versus rotor part relatively in the different positions, because after applying so-called mixing plane approach, these differences are neglected. So in this case, which will be our case, where we have only one segment of the full wheel, stator wheel and rotor wheel, then we need just the segment, and the interfaces must be aligned. The virtual full wheel interface has to be aligned. And the last part, because the STL generation requires the first discretization, then the discretization has to be fine enough to properly describe the original smooth geometry. So this is also important part. And sometimes if you export the STLs from a CAD software implicitly, just save as STL. So usually the STL is really very rough, and for example, for highly curved areas, there is just zigzag shapes, which gives you the huge error in the resulting CFD simulation, because simply you are simulating something different from the original shape. So keep in mind that also this STL triangulation has to be fine enough, and there are many items why it should be so. For example, on the interfaces for the radial machine, where the interface is made by a ring or circular shape, then if the triangulation is pretty rough, then you can see the significant difference at the normals, which are then used for the interpolation from one side to another, and the errors are rising with the rougher triangulation. So therefore, fine triangulation has to be done, and also if you meshing two parts separately and not within as one object or as one solid, for example, in the CAD. So then it may happen that the neighboring patches, which were exported separately, are so-called not waterproof. There are holes at the interfaces because the interface has no point-to-point correspondence. So sometimes if the triangulation is pretty rough, so these holes are big, then the mesh can leak out because of these holes. Yeah, so sometimes can happen then the meshing process is not finished well, because there are so big holes that the meshing tool means that there is no boundary, so it goes through these holes, and then you can see that, for example, some internal pipe is meshed from both sides because there is simply a hole. But if you make the STLs triangulation fine enough, even there are some holes, but the holes has a similar size of the triangulation, so then usually you are safe because the holes are so small, then the meshing tools can't see them, and everything goes well. Okay, so it was, let's say, quick introduction how the input STLs should look like. So in here we have everything prepared. So for example, the STLs of the blade are split into the 4 parts. So I can show you. Okay, I can, for example, can get rid of the rest. For example, here, and for example here we see our splitting. So we have each STL for each part of the blade. So then we can play more with the meshing, the fine meshing at the leading edges and at the leading edge and trailing edge, and so this we have to have at the beginning before we start to work with TCAE. Yeah, so the input data must be prepared in advance. And now let's go for TCAE. So after installation, you will see the icon on the desktop, for example, and if you click on it, you will see the interface. So after clicking apply, we will see several windows, each holding some data to be visualized. Here in the left side, in this pipeline browser, we see each item of the TCAE workflow three, if I can say in this way. And the menus in bottom are the parameters or properties for each item for each item here. So if you clicking on each item, so different menu here will appear. So the main one is the TCAE, which holds everything. So here you can manage the workflow. So here you can run the meshing part, simulation part, you can visualize the result and so on. And in each subsection, in each submodule, in the TMesh, you set the TMesh parameters. In TCFD, you set the CFD parameters. And finally, in TFEA, you can set the FEA parameters. So at the beginning, we will start with the meshing because without the mesh, we can't simulate anything. So let's go here. First item, setup file. So everything what I will do, I can store in a setup file, which can be later on reloaded or load again if you close it, or you can use it as a source configuration file for some, let's say, for example, optimization loop, because you can connect it into any optimization software, tell which parameter will be changing and so on, and you are working just with the configuration file without the graphical user interface, for example. So let me make it full screen and let me save our setup file into our working directory. So I will go to the tutorials folder, Axial Fun Stage, and for example, I will call it as tutorials. Tutorial set our webinar setup. It's better. Webinar setup. Okay, so I have made this setup file for storing all what I will do. Okay, then here are the two buttons, because anytime for any simulation you don't need to, for example, to do the TFEA analysis or TCFD analysis at all. For example, you will just need to create a computational mesh, which will be our case now. So first we need to have the mesh before we start to set up the CFD simulation. So I will unclick both modules to keep just the TMesh. So now I have just the TMesh module, and I can go here for the TMesh item and to set up the meshing part. So let me just maximize this render view for the visualization of the input data and of the geometry. So first of all, mesh output, what I would like to generate is now the mesh for the CFD purposes. So the mesh output will be just the CFD mesh. Okay, then go for the item by item and set up the meshing parameters. So first one is the rotation reference frame. What is it? So sometimes I will use my presentation. So I think about the reference frame, what does it mean? Is described here. So reference frames basically defines the axis of rotational symmetry, and at the same time it defines the axis of rotation. So for example, for the segment case, we need to know the symmetry both for stator part and rotor part. So what is the axis of the symmetry by which the transformation is done to make a full wheel from the segment part? So therefore we need to define two frames, one static and one rotating. And the axis is defined just by the directional vector and the point lying on the axis. So the default one is the x direction, and the point is in the origin in the point 0, 0, 0. So in this way, if you compare it to the input geometry, which you know, then you know also the axis of rotation or axis of the symmetry. So we have static and rotating, which is the default. Then we will go to the components. So here we basically define in the component section. So I will close this one. Here we load both or either external mesh if we have someone available, or input geometry for the meshing. So let's go for that. So at bounding box for external flows, it's not for us for this case. Turbo machinery case, yes, it is turbo machinery case. Scale factor, it's basically it defines the source unit. So sometimes the CAD export in the millimeters, inches, and so on. So these are the source millimeters. Millimeters. Source dimension of your input geometry. So our input geometry is in meters. So we keep it as that the source dimensions are in meters. Number of components. So we will have the rotor and stator part. So we will have two components. And let's start with the first component. So component name, it's up to the user. So let's say the component one is the rotor, because we have the axial fan. So first, if I go in the direction of the flow, then first is the rotor, and then there is stator vane stator. Reference frame, here it denotes that if the whole component is rotating, so basically if the component includes the rotor part, then it must be defined as rotating. Mesh input is directory with STLs, is the default, or external meshes, you can choose here. But we have the directory with STLs. So by this icon, you click and locate the directory where you put the input STLs. So again, TCAE installation tutorial, Axial fan stage, and STLs, and the rotor. So I will click OK. So immediately you will see that the table is filled with all the STLs which was found in this directory. Okay, then what we have here, number of periodic segments. Number of periodic segments denotes how many segments build the full wheel. So here our geometry includes 16 blades. So we will have the 16 segments to make the full wheel ready. So from this, the transformation is automatically computed for connecting the periodic parts and so on. So this is important part, and also then to compute, for example, torque for the full wheel, not just for the segment, for the full wheel flow rates and so on. So everything is then automatically recomputed. So the next step here, we have to assign the type of the boundary. So we have to enable which STLs creates the component for rotor. Probably I have another helping slides. Let's say, I think here, yeah, so the type of the boundary defines, let's say there are, say how many, 6 group of boundary types. I will go very quickly, but I think it's very familiar. So inlet and outlet define the physical inlet and outlets into the domain. So inlet and outlet has no neighbor. It's a physical inlet where the flow goes in, and outlet where the flow goes out. Then we have three types for AMI connection: internal, translational, and rotational. This is applied to a couple of patches within the one component, which are connected by AMI interpolation, and basically denotes 3 types of transformation. Internal AMI, there is no transformation. Translational AMI, it's a translational symmetry. And for our case, where we have the segment which has a rotational symmetry sides, then we will apply the rotation AMI. Yeah. Then we have empty and symmetry, some symmetry restrictive patches which we are not going to use. Then we have a general wall type which simply describes a physical wall, all wall slip, which describes a wall with no friction. I think maybe it's not up to date because now the wall slip boundary condition is defined within the CFD part. Okay, but we will not be using this here. And then we have a special type for the turbo machinery cases where it's, I think, pretty straightforward. There are exclusive names for the type of the wall, but for the turbo machinery purposes, shroud blade and blade suction blade pressure sides, which helps us to refer to these parts, for example, in post-processing setup or or in the name of the patches for post-processing tools. And the last one is inlet, outlet, and free stream interfaces, which are for the inlet, which are used for defining the inlet and outlet from the components, which neighbors with another component. So these define the interfaces between the components. If we know the direction of the flow, then we have inlet or outlet interface. Or if the flow is not known, for example, a closed propeller in the cylinder, then we have free stream interface. So these are the type of the patches. So let's go for it. So let's go for it. A rotor blade leading edge. So we have a type blade leading edge, pressure side. This we have here, suction side, trailing edge. FA just for FA analysis. We don't need it here for CFD purposes. Rotor hub. It's simply a hub. Inlet is the physical inlet. There is no neighbor, yeah, because it's the first component. Outlet is the outlet interface because it must be connected to the stator. And periodics, so here we set this rotational AMI. So these are the rotational AMI patches, and last one is the shroud. So if I click apply after enabling them, so we can see here in the render view under this icon, CFD geometry. If you click the eye icon next to the item, you can visualize it or make it invisible. So this is our input data. By, for example, double click, you can denote which item refers to which part of the geometry. If you would like to see what is inside, you can anytime click here the display part of the setup, and here is the opacity, so you can make it visible, or can make the opacity at some level you want. And now we can, for example, see what is the leading edge and so on. So by double click on the name of the patch, will make this patch visible in the render view. Okay, so the next column to check is the frame. Probably I have another slide here. Yes. So the frame describes if to which frame each part of the geometry belongs to. So if rotating, it means that this part is physically rotating, and if static, that this part is static. I think it's pretty clear. So here everything is rotating except the shroud, because shroud is not rotating here. So I will set as the static. And for patches which are not the physical walls, there is no importance of what you set, if reference frame rotating or static, because in this case both frames hold the same axis of rotation, so it's no matter what you set here. I have closed something here. Here components, sorry, component 1. Okay, so this was the rotation frame. So only you can care about the balls, and which wall is rotating, then the frame is rotating, and which wall is static, then the frame is static. Clear. Okay, what is important, that up to time you should go to the main item in the pipeline browser and save the current setup, because if something happened, you can lose all your setup, or your half hour or 1 hour of working. You can lose, so up time to time go back and save the current setup. Okay, so now we have we have defined the input data, and now we would like to define the mesh, of course. So let me start with which, yeah, how we can define the refinement, or how the cell size is defined, and so I think I have another slide here somewhere. I think this one. Yes. So how the meshing works. So the meshing works in that way that you define the so-called background mesh sizing. So you define the size of the largest cell in the domain. It automatically defines a box which is in which our domain is enclosed. It defines all the cells with the same sizing, which we define here, x, y, and z, the direction and size in that direction. And for each part of the domain of the geometry, we define the level of refinement. So in this way, so we are not defining the proper sizing of the cells, but the refinement with respect to the basic cell size. We call it the cell with level 0. So if, for example, the inlet intersects any cell, and we, or not inlet, for example, here the pipe wall is intersected by the cell, and the level is set to 1, then the cell is split it into in 3D into eight cells of the equal size, and basically the level or the mesh refinement will be higher by level compared to the rest of the geometry. And we have the minimum and maximum level of refinement, so we can define the minimum and maximum is then applied on the highly curved areas with high curvature, and the minimum is applied on the flat parts of each part of the geometry. And also the important part is the internal point, because we have to tell the measure, yeah, right, if we would like to mesh the object from the inside or from the outside. So let start to define the sizing of the background mesh. So let's say, I think the diameter of the wheel is more than 0.5 meter. So let's start with 1 centimeter. So I will set everything to 1 centimeter, and if you click show background mesh wireframe, you will see how the initial mesh for the meshing looks like. I think it's too coarse. I don't want to make the mesh pretty fine, because I would like to mesh runtime, and I don't want to wait for them several minutes. So I will do the mesh pretty rough. Yeah, so this is not the final simulation of any project, because yeah, you need to do many steps, refine more and more, compare the results, and check the results, and to decide if this mesh is fine enough that, for example, the efficiency doesn't change too much if I refine more and more. So let's say I'm satisfied with 5 millimeters, and then let's go to refine the other part. So let's say what we need. Okay, the most important part is the blade. So let's say that the pressure and the suction side, I will, because it's a flat surface, so I will set the level 2. For the blade leading and trailing edges, because they are they are very curved, so I need much more high level of refinement. So let's tell 3 is the minimum, and for really highly curved at the top of the leading edge, for example, set the level 5, and the same for the trailing edge. Then let's say hub is important part, so I will set level 1, the same for the shroud, and the rest I can keep at 0. Okay, so let's try to do this. So we have show background, okay, and the last thing to define is the internal point. So now if you click here, so you have to move this point into the inside the domain, inside the component you would like to mesh. So this is the, let's say this is the sphere which helps you to view the point, so, and the diameter of the sphere, so I will make much lower. Okay, so here is my point inside the sphere. So I will put the point inside my domain. Yeah, so I think now we are in. So this is okay. To be sure, I will save my current setup. And let's keep in this way. Similarly, we will do the second component, which is for stator. So I will quickly set the stator part. Okay, let's say stator, reference frame is static, directory with STLs, which is okay, stator, okay. Number of periodic segments, now the stator has, I think, 12 for our geometry, 12 blades. And similarly, we assign the correct types for each part. So this is pressure side, this is suction side, this is trailing edge, double click then hub, double click, okay, shroud, sorry, the inlet. So the inlet is connected to the rotor, yeah, so it is the inlet interface. Outlet is the physical outlet, there is no other component, and periodicities are set by not translational, sorry, rotational AMI. Okay, the background mesh I will use the same as for the stator, and for now, don't forget, I will define the internal point. Okay, I don't see, so click apply because I don't see the domain. Now the domain is loaded after clicking apply button. So now I can put it inside. Yeah, I think it is inside. Okay, apply, save. Well, anytime during any setup, you can click check setup if everything goes well. And for example, if I click, it will tell me that, yeah, the rotation AMI is not connected to its neighbor, right? What does it mean? Okay, because you have to connect, because it is a couple, yeah, of the periodicities. So here, where is the rotation AMI? So this part should be connected to this part, yeah, because there will be some interpolation to mimic the symmetry of the segment. So I need to right click the type of the rotation AMI. So you right click and connect to the patch. So I have only one neighbor or one other rotation AMI type. I will click this, and if it's connected properly, it will be visualized by another color. So the same for the stator. And similarly, we need to do the same for the inlet-outlet interface, because you can have many components, many interfaces. So always you need to set what you need. Always you need to connect the neighbors. To see the topology, there is a nice map which tells you if everything is connected properly. So now you can see that we have two components which are not yet connected. So I have not done it yet. So let's go for the interface type, right click. Now there is the list of all the components to which can be connected. We have only rotor component and one patch of the outlet interface type. So it's rotor outlet. If I click now apply, you can see that now there is smooth path from the inlet to the outlet over two components. So this shows me that everything is connected properly. So let me save the setup. So now we have some guess for the component parameters, and for component 2 I have just connected to be topologically correct, and we will set up the refinement levels after we will be satisfied with the meshing of the first component, because then we can set the same parameters to get the similar topology of the mesh, similar refinement. Okay, and the last thing, so now I would like to move to the meshing, but the last component to check is the parallel run to speed up the meshing. It can be parallelized. The default is 1. So my computer has, I think, 10 cores. So let me use 10 cores for the meshing. Okay, another click to check setup. Okay, now we can see okay, setup is okay. So now I'm going to try to mesh following our setup we have made. So director name mesh test, or let's say webinar test, for example. Apply. First of all, we need to hit the button write case. So now it will write all the necessary files on the disk, and there is a button to run all, but now I would like to go just for the T-mesh and to run the component rotor. So we can click the build button, and now the meshing meshing is now the TCAE is generating the mesh, and hopefully my mesh is set properly. Okay, it's finalizing already. Okay, and the mesh, I think it will be ready in a second. Yeah, whenever this box is green, it means the mesh is finished and successfully finished, in sense of there is no big error in the meshing process. And now we can hit the show button to visualize the resulting mesh. So I can disappear the input data. So this is CFD geometry. Where is it? CFD mesh here. If you click it, and you can, for example, visualize the surface with edges to see the topology. Okay, now that there is still the visualize the internal point, so I will get rid of it. And can go back here. Yeah. So this is our meshing. Okay, it's pretty coarse, but I think yeah, the leading edge and the trailing edge is meshed pretty fine, let's say. But if you can see, the periodicity is pretty rough. So let's make another loop to improve the meshing of these tic-tac shapes of the periodicities. So we can go back to the T-mesh. So one option is to refine the whole periodicities, but we will lost, or not lost, but we will gain a lot of new cells, which will increase our mesh. So we can do it, for example, in a more clever way. So I think if I borrow another slide, I think it's somewhere here. So it's not this one, it's this one. Yeah, there is the option in the advanced menu to automatically generate so-called feature edges, which is basically the edges connecting two parts which are split by sharp shapes, let's say. There is a parameter how big angles should be, or by the angle how sharp edges should be extracted. So 0 for no edges and 180 for all edges. And based on these edges, we can then set the level of refinement, for example, only on these edges. So for the cells which are intersected by these edges. So let's go back. So as I already mentioned, in the advanced meshing options, which is here, in the STM manipulation, here is the feature edge include angle. So we would like to export all the edges which are here. So let's say I will use very high angle, for example 165, and inside the castellated mesh parameters, here the feature edges level. So this is basically how I can say that using these edges, if the cell is intersected, so refine to my given level. So let's say I will use the level 2. So let's try if it improves my mesh. So again, I save to be sure to keep my setup. I will write the case because I have changed the parameters, so I need to write the new parameters again and rebuild the component. So again, I will click the rotor. So now the solver is generating the mesh. The meshing solver is generating the mesh. So we will wait a few seconds. So now the mesh will be a bit larger, and I hope after few seconds the mesh will be done, and yeah, I think it's already almost at the end. And always here in the log you can check, for example, for how many cells we have, for example, now. So number, it is, here are the mesh statistics, number of cells. So we have 160,000 cells at the moment. So let's show the mesh, and you can see, yeah, now we have all these edges refined, yeah, and the mesh looks pretty acceptable, let's say, for the CFD simulation. So in a similar way, now we can set up the stator part. So let's go for the component 2, and I will use a similar level of refinement, let's say, except the leading and trailing edges, because the let's say blade is more thick, so there is no not so highly or sharp tip of the leading and trailing edge compared to the rotor blade. So I will use a little bit lower level of refinement for the edges. So let's say 2 and 4. Pressure side will be the same. Trailing edge 2 and 4. Hub we set 1, I guess, right? 1. And shroud also 1. And the same thing for the feature edges as we described. So component 2. So 165 was a good choice, and feature edges level 2. So we can keep in this way. Go back, save, write my current setup, and build the stator part. So you could see that we didn't change the parameters of the rotor. So if we write the case, so the rotor doesn't change the color, it's still in green because the resulting mesh still corresponds the setup. If you change the setup of the rotor, it will be highlighted by changing the color, and then you have to also remesh also the rotor part if you change the parameters of the rotor part, but I think it's obvious. So now we can visualize the rotor part, so I think it's pretty okay. Now I remember that the last thing I haven't said and haven't commented is that how this interfaces, the inlet and outlet interface, has to be connected. So there are, or numerically, how the information will be transformed over the interfaces. There are two approaches. First one is with the zero mixing plane. So it's then called periodic AMI. So there is some, let's say, kind of interpolation without any averaging. So it interpolates the data as they are, but of course it is mapped on the full wheel geometry. Some magics are done, and then the interpolation can be done also for these non-aligned interfaces. But the usual approach for axial machines are to use mixing plane approach. So it splits the interfaces into the radial strips, into the rings, let's say, and then the averaging is done over these rings, and the information transfers as an average value from one side to another. It's so-called, I think, stage in the CFX. I think it's a similar setup to connect two segments. So for example, let's say we have a rough mesh. So I will set that we will have the 10 mixing planes to make the connection between rotor and stator. So this is the last item to set, both for component 1 and component 2, but these are connected, so automatically the number will appear also on the other side. Okay, save. So I think we are done for now. And the last thing, not the last thing. So the mesh is ready. We are satisfied with the mesh, and now we can go for we can go for the CFD setup. So I will enable the TCFD module now. Okay, hit apply. Okay, I have several windows here, new windows, so I will, I think, close some of them. I don't need this. Let's say, okay, I will have this quantity monitor available. Then we will play with the render views. Okay, I will go here. So now we have the item TCFD, and now we would like to set the CFD simulation. So pretty quickly, so simulation type is a fan. So there are several types to be defined or to be used: pump, water turbines, heater turbines. So it depends on the application. So it's always focused. So now we have a fan. So we will use a fan. In the physics, we will go step by step. So in the time management, here within the one CFD simulation, we can simulate several physical conditions, for example, different flow rate, different pressure drops, and other flow regimes, for example. We'll go for steady state. You can also go for transient. So steady state solver. So at the end, we will have a steady state solution. We can use also the transients, but its better application is for the full wheel geometry to have the all information about the simulation, and then the rotor wheel or rotating part are physically rotating, and the solver is transients. So it's much more complex. It requires more time to simulate, and so on. So let's stick with a steady state simulation. The speed lines hold the information about the rotation speed. So for example, if you need to perform the simulation for different rotation speeds to have some, for example, typically for compressor, to have a compressor map. So then you can set several speed lines, so several rotation speeds within the one simulation. But this fan runs at the constant RPMs. So we will stick with the one speed line. And speed line points, so how many different conditions we would like to simulate. So let's say we would like to simulate, as an example, 3 different conditions to, for example, reveal the highest efficiency point, for example. The default number of iteration depends on the application, depends on how many cells are there, depends on the complexity of the flow. So we have a rough mesh. I will be using first order scheme, so I will stick with 500 iteration. I think it will be okay. Fluid parameters, because the axial fan has a slow flow speed, the compression number is almost 1 or a little bit above 1. So I can expect the incompressible flow, incompressible physics. It's much more faster if your physics allows it. So always go for incompressible, because then the simulation is much more quicker without any loss of information. Free defaults, you can set some dynamic and reference density and reference pressure. So I will stick with the defaults and with the atmospheric pressure as a reference pressure at the inlet, so it sucks from the atmospheric condition. We can have some multi-physics for another application like passive scalar, porosity zones, calculate edge for human comfort within the buildings, for example, include gravity just only for, I think, heat transfer applications. So I don't need any multi-physics. Turbulence, I will stick with the K omega SST model, which is I think the choice number 1 for these general applications. Rotation reference frame. So here, based on what we have defined in the T-mesh, we will just define which frame is rotating, usually the rotating frame, of course, and what is the speed of the rotation. So I think here I have some slide to describe this, I guess. Let me show the slides to better explain how to define the direction of rotation, how it is defined. So the rotation speed can be also a negative number. It means that it sets the direction of the rotation and it follows the right hand rule. So if your thumb points the the direction of the axis. So then your, let's say, cross fingers or curved fingers shows you the direction of the rotation. So for our case, oh, sorry. So for our case, this is the rotor. It goes in this way, right? It rotates. It must rotate in this way. This is the axis in positive in x. So the positive direction is this. Yeah. So the number here will be positive, and this axial fan operates at 300 RPMs. All right. Okay. Let me save my current setup. Go back for TCFD. So we will have 3 points. We set the rotation frames. So the next step is the simulation. So within the solver, what we can set. So how many processors? I have 10 cores, so I will use all of them. Numerical order, I will start with the first because it's much more faster, and I'm not sure if my setup is correct. So always start with the first numerical order, and if the simulation goes well, then you can go for the second. Otherwise, you don't know if the numerics crashes because of the second order scheme and while flow, or if you have some mistake somewhere. So it's always good to start with the first order scheme, and if everything works, then go for second. The convergence check. Here you can here you can set the convergence tolerance and averaging window for the averaging of the solution, because still it can oscillate, and I think I have a slide for that TCFD simulation. So I think, yeah, this is the slide which explains. So even we have the steady state simulation, so we will expect a steady state solution, but still it is a numerics which can oscillate for many reasons. So if we, for example, look for the efficiency, and we have a rotational machine, so we can see some oscillation in the result, in the intermediate result. So the purple line here shows really the results after each iterations. Therefore, the result depends on where you stop the simulation. If you stop here, the efficiency will be 77.5%. If you stop here, the efficiency will be 1% point lower. So this is not what we want, even for example for optimization loop. So there will be difference if we just change the number of iteration, or if I change something. So what we are looking for is the average solution. So therefore the averaging window defines the averaging window, the window over which the instant values are averaged. And what we would like to see is that the averaged value, for example, for efficiency, is constant. And then we have a robust, stable solution, independent of where we stop the simulation. So this is what we have, and this is why the averaging window parameter is here. So I think usually I use some 20 or 10 or 20% of the overall iteration. So let's say 100 from 500 of overall iteration is a good choice. And convergence tolerance, there are some parameter which looks for the convergence. So it looks for the efficiency and other parameters. And if the efficiency doesn't change over this averaging window if it changes by less than this threshold, then the simulation is stopped automatically before the maximum iteration is reached. So let me stick with this convergent tolerance, so 0.1%, for example. I think this is the most important part. Some other parts are not important for usual user, because they are set to some default and robust values, some controls for the solver, for the linear solver, and so on. But the most important part is one of the most important part is the boundary condition. So here we basically define our problem, what you would like to simulate. So there are several options. how to set the boundary condition at the inlet and the outlet. At the outlet, usually there are several, let's say, standard couples of boundary conditions. Let me go for, I think here, yeah, this is the, let's say, the short overview of a standard couple of boundary conditions. For example, total pressure at the inlet and static pressure at the outlet, or flow rate velocity at the inlet and static pressure at the outlet, or total pressure at the inlet and flow rate velocity at the outlet, or total pressure at the inlet and so-called outlet vent, which was designed for the compressor and fan applications. So this is what we will be using. So the total pressure at the inlet and outlet vent at the outlet. So let me stay here. So total pressure at the outlet, we are in the incompressible mode. So the solver operates in so-called kinematic pressure. So the pressure divided by the density. So we can treat these values as the reference values. So relative value. So relative value is 0 pascals, which will be then afterwards, after the simulation is finished by our post-processing tools, will be put back into the real pascals with the reference pressure 1 atmospheric at the inlet. So basically, to the all pressures everywhere will be recomputed back into the Pascal and added this reference pressure to all parts. So as a result, at the inlet, we will have 100,000 pascals as a result. At the inlet, we also have to set the turbulence quantities. So for example, if we do not any special formula to set, so we have several choices. I think, for example, the more straightforward is the turbulence intensity and hydraulic diameter. So turbulence energy intensity is the how many percents the percentage of the fluctuation of the flow. So basically standard turbulent energy intensity in percent. So 5%, for example, for internal flow is okay. Hydraulic diameter is the diameter of the inflow channel. So here we have something like 0.5 meters, so half a meter, and the reference velocity in this case, I think it's something like, could be, let's say, 10 meters per second. All right, so it automatically evaluates the proper turbulent quantities at the inlet, and at the outlet, as I already mentioned, we will use the outlet vent, which is a special boundary condition designed for this type of applications. And just to see what it means, yeah, typically, for example, for compressors or blowers. So the outlet vent is this. So it's kind of a virtual valve which you slowly closing the outlet. So you are increasing the pressurize of the blower, and it is done by this formula, and we are adjusting the parameter R. So it's somehow we multiply the kinematic part by this R factor, and P0 is the basic pressure. So for our case, so base pressure is 0 because we are using the 0 as a reference pressure. Some kind of relaxation to make this boundary condition robust, because it changes over iteration, so it must be somehow relaxed. And the max pressure is the threshold. So 50,000 is okay for our case because we have the Axial fan which has less than, I think, 10,000 Pascal, the maximum pressure drop, and I think even lower. And the resistance are the air. So let's say it depends on the application, but for the axial fans with a low pressure ratio, it is just in sense of low numbers, 0, 1, 2 or something like that. So if we set the R 0, so from this boundary condition the R is 0, so it is out. So it's simple static pressure at the outlet, which equals to the total pressure at the inlet. So there is no pressurized in the flow in the fan. So I will start with this, and I think for this fan, I think something like this could be the proper parameters. I think the best efficiency point is somewhere around the 0.5, I guess. Just for this webinar purposes, we will set in this way, but usually we set these numbers based on previous experience with each type of the simulation or each type of the geometry. Okay, for the walls, yeah, here it is as what I have mentioned. And now the slip, the wall with friction and without the friction you can set here. So the default setup is all walls are with friction, which is okay. We have no interface condition here to be applied. So walls and interface condition are of no meaning for this case. And the initial condition must be set to something meaningful. Yeah, so for example, I will use the inlet turbulent values as initial to don't care about them. The pressure, I will set zero pressure because it is the inlet, so it's a good initial point. And velocity, I will set, for example, 10 meters per second as the initial velocity in the x direction. Okay, and the last thing is the report to define, because we would like to have the results. So the report will be automatically generated and will include all important parameters of the flow from the result. So the efficiency probe holds basically what we are interested in. So from which parts of the domain we would like to evaluate the efficiency, the pressure drops, and so on. So usually from the inlet to the rotor and outlet from the stator, but you can also, for example, evaluate just the rotor part if you want by setting the outlet from the rotor here. All the torque patches, so let's say hub is also rotating, so I will include also the hub. So the torque will be evaluated from all parts of the blade and from the hub. You can also set another, for example, forces to acting on the axis, for example, the stator part to see the force in X, Y, Z direction, or some other forces. For example, to do so, you will simply click which part you would like to evaluate. So, for example, the stator part, and it automatically evaluates the forces in X, Y, Z direction. So we basically would like to have the axial force, which we get from the default setup we have here. Then we can also visualize some automatical post-processing tools. I think I have mentioned it many times. You can find it on the web, so I will not bother with. No, I don't want to bother you with these turbo machinery things. So as an example, I will do some meridional average post-processing. So we will just pick which component to visualize and which field. So let's say total pressure, for example, and that's all. You can also follow any point value from any part of the domain. So you can define a point from which you would like to follow some parameters, and these are some advanced or miscellaneous functions to write the surface quantities for another usage, or write mesh and results to CGNS for post-processing in a different tool than ParaView. Okay, so quickly run the simulation. So I will save the current setup and go for, okay, I have closed all the parts of the menu. So now I need to write the case. Okay, I have missed something. So the wheel diameter, okay, for the rotating component is not set. So I have seen here, yeah, that for some post-processing tool, the fan needs to know the wheel diameter to compute, I think, some dimensionless parameters for fans like the flow number or something like that. So wheel diameter, I think, is something like 0. I'm not sure, 56, I guess. We can, okay, we can measure it. I think if you click here, click somewhere here. So what is the Z? 0.27. Okay, so this is the radius, so it's 54. All right. So let's go back, save, check the setup. Okay, now case setup is okay, perfect. Write the case. And let's say I will click run all button to run everything within one click. So I will click run all. So it will start the meshing again. But I think it was not needed, but I just would like to show you that by run all button, everything is processed automatically. Otherwise, I needed to click the merge button to merge the both component into the resulting mesh, which includes both components, and then run CFD calculation. And after the calculation, for example, click to here to post-processing to generate the report with all the results. So by clicking the run all button, everything is done automatically. Well, so now I think now is the time to get from the render view into this line chart view, it is so called. So here you can, during the simulation, you can follow any quantity you want. And because, okay, I have probably closed the window, so I will split the window here. Now you can click here the line chart view, and here under the TCFD item, you can visualize, for example, the residuals. So if I click the residuals, so you can then follow the residuals during the simulation. And back to the quantity monitors, if you click quantities and go to display, you can check any quantity you want to follow. So typically, I don't want to see the mass flow at the inlet and outlet. I would like to see the efficiency and the average efficiency, which is, yeah, here, efficiency average and efficiency instant. So now you can follow the efficiency runtime. Okay, so we will wait for a while for the results, and meanwhile, I think I will try. Okay, I think I have saved everything. And meanwhile, I will also set the simulation for the finite element analysis. So first of all, we need to set the finite element mesh, which is pretty straightforward compared to the CFD mesh. So here we will load just the solid of the STL, which holds the solid in, or which holds the information about the solid of the blade. So I will go to the rotor part, and here we have available the here rotor blade FEA. Then for setting the parameters for FEA, I have maybe some slides to show you. Okay, I think it's somewhere at the end. Yeah, final element, and this is the analysis. This is the input requirement for the STL. So there is maybe only one parameter that it must follow the solid, and the solid, because it's solid, it must be waterproofed. Yeah, so the STLs must be waterproofed for these cases, and it must be really good alignment between the CFD, of course, mesh, and CFD input geometry and CFD mesh and the FEA mesh. In other words, FEA input geometry, because it is automatically mapped. This FSI connection is done from the CFD results to the FAA results. Okay, so you can see that the second point is now simulating. So first point has something like 70% of efficiency. But back to the FAA analysis. So I can go back here, can click apply and visualize. Yeah, so this is the input solid. Yeah, so this is going to be meshed. There are just two parameters for meshing. There is the maximum size of the tetrahedra and minimum size of the tetrahedra. So let's say I will make it pretty rough to make it quick. So I think 1 millimeter will be the smallest cell, smallest tetrahedra, and H max will be the 2 millimeters. All the other parameters are some optimization or not optimization, some parameters of the solver, of the NetGen solver. So basically we care just about these two parameters and input STLs. So I will click apply. I will save the data. And now we should wait for the results. So for example, now if I go, yeah, if I go a little bit lower here, I can skip to the next point, yeah, because it's already converged from my view. So I can skip for the next point by the skip button. And now we will just wait a few seconds for the simulating of the last point, because we have to wait for the simulation. We can't run the meshing of the FAA before some other simulation is done. So you can wait for a while, and then and then we will generate the FAA mesh and we run the FAA analysis. Okay, well, maybe meanwhile we can also set the, I can activate the FAA module. So now we can see we have also FAA module here, and now we can set the FAA analysis, which will be also much more faster. So we don't need any thermal because we have any temperature here. We would like to do fluid structure interaction, of course, because we would like to map the results, the resulting forces from the CFD onto the solid and perform the kind of fluid structure interaction, of course, and the stress analysis. So the source for FSI is TCFD results. Patches for FSI mapping are the rotor blade, of course. So we have rotor or the rotor blade parts. Rotate with TCFD frame. We can also include the rotation into the solid. Yeah. So we would like to mimic the rotation of the solid itself as well. And I would like to use the relative pressure for computing forces. It's always better option than use the absolute, because then it's much better because the forces are then closer to the reality if the object is not flying in the, let's say, because some parts are not mapped properly, because for example this solid here is not part of the COD simulation, and it's like then that there is no pressure. It's like the zero pressure, no forces, and here are basically large forces if we use absolute values. So always better to use the relative pressure for computing forces. And we would like to also use the model analysis, which will give us some frequency analysis of the eigenvalues and eigen stress, let's say the maximum stress for the eigenvalues of frequencies. And we would like to have the three eigenfrequencies, the first three eigenfrequencies to simulate or to evaluate. Then the solver, I think solver for solving this system, the resulting system. So the default is direct and finite element order second, so it's common default value. And use nonlinear equation, you can use it if the deformation is is pretty large, but in this case the deformation is pretty low, so we can stick with a linear equation which runs faster. Material properties, the default is the steel, so I will keep as a standard steel. And the boundary condition here, we define where to fix the region, because we have to fix the blade something. So the blade will be fixed, let's say, in this solid, in this part, which is really fixed to the hub, and we can set it by the simple shapes. Here the cylinder, so I will define the cylinder which is intersecting this part of the blade in the lower part. In the next version, there will be also highlighted this region, which is not yet implemented in this version. So the standard parameters for this case are, I think, 0.147 is the Z direction. Okay, here, don't ask me again. It's somewhere, yeah, it's somewhere here, if you can see, yeah, 1.47. So all the part below will be the fixed region where the blade is fixed to the hub. So this is clear, and the direction of the cylinder is Z, right, and the origin somewhere below. So there is just the common part of this cylinder, virtual cylinder, with our geometry. Okay, so I will click apply, and I think our simulation is done meanwhile, which is great. So if I go back, you can see that the simulation is done, the report is done. So meanwhile, I will save my setup. I will write the case. I will run the meshing of the FAA. Okay, so build FAA mesh. I think it will be okay. Where is my log file? So now the meshing for FAA analysis is okay. Is performing, and now mesh is successfully done. Okay, perfect. So FAA mesh is done, and quickly I will run the FAA analysis, which is here. So run FAA simulation. Okay, and the simulation is running. Okay, so meanwhile, I think we can visualize here in this HTML view, we can visualize the results of the CFD simulation. So I will click into the report. So we can see that anytime after the simulation is finished, the nice report is generated in HTML format. You can open it anytime here in TCFD, or you can open it also from the case itself. So here, webinar case, TCFD, here's the report. So you can anytime open it in your web browser, for example, and watch the statistics. So some convergence of the flow rates, convergence of the residuals, details about the mesh, about the quality of the mesh, fun characteristic, efficiency. So here we have, yeah, we really hit some point near the best efficiency point, so we can read the maximum efficiency of our system. We can also check the convergence rate. So for example, here maybe I would add more iteration because the constant value is not reached. So maybe the first point needed more iteration to converge fully. Torques, axial forces, force coefficient, or let's say forces of the stator part. So here, for example, forces of the stator, and so on and so on. So many parameters. I think we have a detailed discussion in the previous webinar, so it will be really quick. So this is done automatically. You can also anytime visualize the results. So if you go here, and if you show the CFD results button, so let me click just, I would like to see static pressure and only, for example, on hub the rotor, let's say. So check these items. Okay, get rid of the other parts. And yeah, here is just the contours, for example, for the results of the first point of the static pressure. Okay, the times runs very quickly. So let me finish with the FA analysis command. So the same report as we have for the CFD, you get also for the FEA. So we can visualize the FEA report, which is not yet generated. Sorry, because I didn't hit the run all button. So now, where is it? FEA report. So I need to analyze, generate it first. And similarly, I can also visualize the results. So let's say I will choose the second results from CFD, use fluid structure interaction, apply to the FA analysis, and I would like to see the stress and displacement values, for example. So I will visualize these results, click apply, and meanwhile, the report of FA analysis is here. You can browse it and you can check what is the maximum displacement, what are the eigenfrequencies. So let me quickly go through here. So basic statistic, mesh statistics, and information about the simulation, just 17 seconds. Static analysis, so here is the maximum displacement, this is much more than 1 millimeter. Maximum stress, which is somewhere here. Minimum displacement, maximum principal stress here, yeah. And frequency analysis, what are the eigenfrequencies and what are the deformation for these eigenfrequencies and stresses. So all of this information are here. And the last thing, as I mentioned, we can visualize the FA, for example, displacement, distribution, and last thing maybe to show, because it's really too late for today's webinar, we can use the warp by vector filter and really visualize or magnify the displacement of the mesh, if you can see. So this is the original shape. And if I scale factor by 100 the displacement, you can see how the blade is deforming. Okay, so I think I have shown how to work with the standard geometry, standard case from very beginning. So if you get the experience with it, you can get the result within an hour for a simple shapes, and you can really play around with all the parameters, all the post-processing tools, and get the results on one place in the HTML report, or immediately on your disk in the case folder, also tabulated in the CSV file, which can be then, for example, open in the Excel sheet and get all the parameters for the post processing, like efficiencies, power, torques, and so on for each simulated point, for each flow rate, and so on. So the tool is really cool. It can be used for really large simulations, large applications, to analyze everything what you want by any resources which you have. So I think I'm more than 53 minutes after original 1 hour long webinar. So I hope Luboš is still there on the other side. So Luboš, are you still there?
Yes, I am. Thank you, Radek. Yeah. Thank you. It's time consuming, but it was live. It was really from scratch, so it's certainly there's a value in it. So thank you, Radek, for your contribution.
You're welcome.
Yeah. let's finish the webinar. So this is the live part. So Radek showed all the stuff. Thank you for it. And now it's time for Q&A session. So we are running a little bit out of time. So let's pick a few representative questions. So you can ask questions. So we'll give you a couple of seconds, and then we will pick a couple of reasonable representative questions and answer them. And don't worry, all the questions will be, all the relevant questions will be answered later via email. Okay, so give me a second. Yeah, we have quite a lot of questions here. So Radek, feel free to interrupt me and pick one. Yeah, it was quite detailed. So yeah, a typical question all the time is the webinar recording available? Yes, it will be available. It will be everywhere. We will send you an email. It will be on our website, freely accessible for anyone. So don't worry, it will be on our YouTube channel. So and also we can send you a video file if you like. So certainly it will be available. Yeah, I see.
Okay, maybe
So
one
far I'm
question.
seeing. Yep.
Okay, can I
Yeah.
interrupt you? Okay, does it make sense to set both inlet and outlet condition to total fixed pressure of 0 pascals? Well, it makes sense because it's the condition where the fan has no pressure, almost no pressure rise, right? So it just blows, but it doesn't generate the pressure drop. So it makes sense because at the inlet we have total pressure of 0, and at the outlet depends on the flow, but I think the flow is a little bit higher, so it basically generates a little bit of the pressure drop, but we can understand it as that the fan just put the flows but doesn't generate any pressure drop, or it just, yeah. So every energy is put to the flow rate, not to generate the pressure drop, as I understand this.
Okay, thank you. So yeah. So that's Milan is asking, have you coded the FEA code solver? No, not at all. It's Calculix, so it's not a secret. It's we just take open sources and we do the best possible with them and make them communicate each other, and we are creating additional stuff for them. So the FEA solver is Calculix. The CFD solver is based on OpenFOAM, and yeah, such a stuff. So it's there's a list of used software on our website. So you can, if you open for example, OpenFOAM for Windows stuff, you can see all the versions and packages. There is about, I don't know, 45 open source packages in the bundle in the TCAE. So it's Calculix for TFEA. Can you code do fun aeroacoustics? Yeah, acoustics is a big thing. We are running a large project at the moment in the company. We are doing comparisons. We are doing this at the moment with the stuff, and we hope we will be able to deliver aeroacoustics module this year, later this year. So we hope everything will be going well. We have one strong condition: it has to be usable. We are not going to deliver something which tells you have to use LES and run it a couple of months on a cluster. So we are looking for a usable method. That's the bottleneck in our current development of aeroacoustics. It has to be heavily usable for normal users on normal simulations. Speaking about that, the new version will be released in February. There will be a couple of new capabilities, but there will be most of all new improvements. I mean, new versions of all open source versions of packages. So there will be all new versions of OpenFOAM and Calculix, and a couple of new features. And likely in September there will be again a big release, a big major release with new features. We are on a way to deliver optimization module, and hopefully the acoustics will show itself to be usable. Radek, can you see some good question which is representative and you would
Well,
like
there
to
are
answer
many
it?
of good questions, but maybe we can postpone for the email communication because it's almost 5 o'clock. But maybe the last one is parallel calculation possible for the inlet outlet interface with mixing plane. So basically, this method was set up with mixing plane and in parallel. So this was the application of what you have asking for. So mixing plane and parallel calculation are implemented in our implementation in our solvers. So yeah, it's possible.
Okay. Yeah. There are a lot of questions. We have to quit somewhere. Let's make it now. So I'm closing the Q&A session. Don't worry, we will answer all your questions. We will read them and answer them. So no worries. And I think it's time to conclude. There's a new version coming in February. Did I? Yeah, I said it. So there are a couple of improvements. There's the simulation score, a new, completely new convergence check approach. There will be you can convert, you can monitor convergence based on quantity you pick and set the tolerances and everything. So it will be much efficient, not to waste precious simulation time. And yeah, I hope we will make it smoothly delivered to the market in February. And this is gonna be it. So follow us everywhere you can. This is the almost the last slide where there you can see some brands of those who already share our visions with us. So we hope you will, or some of you who still did not join us, you will join us. We are one big family. We never leave behind anyone, and the bigger we are, the stronger we are. So we hope you will join us sooner or later. And I think this is really gonna be it. We would like to thank you for your attention. Radek, is there something you would conclude?
Well, thank you for watching, because all of you who see these slides are really tough to see.
Yep.
2 hours webinar. So thank you for watching, and we are looking for any question from you, any application for the trial version. We will help to set up your case if you want. We are open and we are here for you. So thank you and have a nice day.
Yep, the same from me. Feel free to contact us. We will gladly support you. It's our job and also a pleasure. Yeah, I guess I will leave you with that. So thank you for now and bye bye.
Yeah, bye bye.